All right. Good to see everybody here. Welcome to our talk. We're going to be talking about building a great data ecosystem and foundation to power AI today. But we'll start off with introductions. My name is Marty Andolino, VP of Engineering in our Enterprise Data Organization at Capital One. I'm responsible for data pipelines and governance, meaning I operate some of our most critical real-time data platforms at scale and have some of our critical data governance services as well. I've been at Capital One for about 10 years, the first 8 of which I spent in our bank technology organization and spent time supporting retail experiences, marketing, fraud, data engineering, and architecture. It was a great lesson learned on how to apply and use data at massive scale in real time to solve customer problems. Professionally, I enjoy solving a hard problem, building massive and scalable systems, driving great customer outcomes, and most importantly, building high-performing teams and enabling our brilliant technologists. So a shout out to my eData teams, and I'll pass it off for an intro from Kajal.
Thanks, Marty. So while Marty and his teams allow large volume, variety, and velocity of data to come in, my teams and I have the simple task of building cost-efficient and performant storage solutions. And with that, my name is Kajal Wood, and I lead the enterprise data platform teams, particularly focused on data storage and consumption. Super excited to be here. I see some familiar, friendly faces and some new faces. So ready for our session.
Great. Thanks, Kajal. All right. We'll talk about today's agenda really quickly. Capital One's tech journey that has taken place over the course of the last decade plus, and how that's enabled us to scale AI and ML. We'll talk about our data principles for AI and how good data can be a foundation for good AI, while bad data can be an impediment for AI. I'll talk about how we produce great data from the data producer lens. Kajal will talk about our data consumer experience and some key takeaways to wrap up. First, Capital One's technology journey. We started out over a decade ago and rebuilt our tech stack from the ground up internally, using open source and building our own technology, being early adopters of APIs and microservices. Next, we went all in on the cloud, so we focus less on managing infrastructure and operations and more on delivering value. We actually have, as proof of that, a serverless first agenda where we really look to serverless compute and managed services to give us great value and, again, focus. When I started at Capital One in 2015, I was one of a handful of AWS certified engineers. Fast forward to 2024, and we have thousands of AWS engineers with at least one AWS certification, making Capital One the third most cloud-fluent AWS customer, including Amazon itself. Off the backs of near infinite storage and compute that we could get in the cloud, we rebuilt our modern data ecosystem to operate at scale and in real time. We converged to enterprise platforms. So within Capital One, not just within the data, AI, and ML ecosystem, but other technology domains as well. We scaled and gained economies of scale through our enterprise platform agenda. We transformed how we build software with a DevOps mindset, and you build it, you own it, but also enabling anytime, anywhere deployments. And lastly, we built an organization of over 14,000 talented technologists, our most important step. So all of this technology first agenda and strategy that's occurred over the last decade have positioned us to use AI and ML at scale to serve our 100 million customers. So is all of that setup and technology first agenda has positioned us well to use AI and ML, including recent generative AI innovations? We've been using AI and ML for several years, both to enhance our customer experiences and our associates' experiences alike, protecting customers from fraud, optimizing user experiences, or helping our agents service customers. But there are three things that will help enable AI and ML foundation. First is your tech stack needs to be nimble, flexible, and elastic. Your data ecosystem needs to scale, be well managed, and, and deliver data in real time. Lastly, I'll allude again to the talent. So having the talent to understand how and where to use data, AI, and ML, and the skills to deliver on that agenda. Now let's talk about how AI and data play off of each other and have a compounding impact or a flywheel effect. AI can help us build optimal user experiences and customer experiences that are more personalized or able to reach our customers to drive better engagement. That better engagement can allow us to see better data insights about those experiences and feed our models with better data to create better AI. So there's a flywheel and compounding impact where the better data you have, the better AI, and vice versa. Let's talk about the 3 V's of data complexity in the world: volume, variety, and my favorite, velocity. For volume, we all know that data continues to grow at a rapid pace. According to Statista, the amount of data in the world has doubled over the last 5 years. And by the end of this year, we expect there will be 147 zettabytes of data in the world. So I tried to picture myself, what is 147 zettabytes? So I did like a little bit of an exercise back of the napkin to say, if you took a piece of paper with some text on it, about 5 kilobytes of data, and stacked 147 zettabytes of data, you'd be able to go to Mars and back over 10,000 times. For those that are more digitally inclined, I think it equated to something close to 200 million years of 4K video. So the amount of volume continues to grow at a rapid pace. Variety. I know myself, and I expect many in the audience, to deal with structured data, which is a complex endeavor at scale. But according to MIT, 80 to 90% of all data is unstructured. So things like video and sound and images and unstructured documents continue to be a huge part of the data ecosystem and something we can't ignore that will help feed AI. The last is velocity. I'll tell a little story early in my career. I used to carry something similar looking like this called a pager, and every once in a while I would be woken up in the middle of the night. A data issue would happen, I'd fix the issue, and I'd go back to bed. But other than being woken up in the middle of the night, there's no major customer issue. But today's digital business demands access to real-time data, sometimes in the range of 10 milliseconds, right? That's 10 times faster than the blink of the eye. But instead of this being a niche area of delivering real-time data, it's really becoming the standard. But when I present data in real time to our customers that may not be accurate, that'll leave a lasting impression on our customers, a negative customer experience. So much worse than me waking up in the middle of the night. So I've left an impression with you all with the agenda earlier, the data quality issue. All right, let's talk about some interesting stats around data that really show how AI can impede or bad data can impede AI. So around data quality, 64% of data and analytics professionals cite data quality as a top integrity challenge, and 52% of IT professionals report struggling with structured data for machine learning. So we're not even in the ecosystem yet of unstructured data, but we're still struggling with structured data. So we have data quality maybe about metadata and how to use and organize this data. And then that time spent on data quality, instead of our high-value ML and AI engineers and data analysts looking for new and creative insights or creating new models to unlock customer experience, they're doing things like fixing data, validating, doing additional checks. So not a high-leverage use of time. But it's not just data quality. 62% of IT professionals cited real-time data access as requiring the most attention to AI. Now, reflect on a conversation I used to have with a colleague that whenever we create a customer experience or a product or a feature or a platform, we want the definition of done for that to be able to emit data in real time. Lastly, 68% of data is untapped in an organization, which tells us we're either producing data that's not valuable or duplicate or not necessary, or we have a huge missed business opportunity where data may not be discoverable, have the right quality, have access issues, or be untrustworthy. Lastly, is the data lifecycle is complex. Some of you may have seen a chart like this in your past, where data it can be inherently complex, the data ecosystem. So there could be lots of hops within a data ecosystem where those hops don't consistently drive lineage or have a data quality standard. They may not have consistent SLAs or a consistent bar around our data management and governance practices. But within this complexity, it makes it very hard to trust data. So we talked about how good data can help generate good AI, and that there are many impediments with AI when we have bad data. So I'm not going to go into all of the reasons on how good AI is created. There will be other sessions for that. But I think what we can say confidently is good data is a foundation and necessary ingredient to good data. So we'll talk about 3 principles we think apply to producing good data and consuming good data. Self-service. We want to give our data community the tools, access, and discoverability to quickly onboard data and to be able to use it effectively. Second is to automate. So there are a lot of steps in the data process we just talked about. Gathering lineage, executing data quality, having SLAs. We want to bake that into our processes and capabilities. And lastly is scale. Data for AI can't work without massive scale, and point solutions isn't something that will scale well. So I'll be talking about the data producer experience today, specifically around application engineers who may be deploying an API to emit data in real time, user logins, transactions, account updates, et cetera. And Kajal will be talking about our data consumers, ML engineers, data scientists, and data analysts. So let's talk about the data producer experience. We want to start with a user experience for our data community to easily produce and onboard data. That should be intuitive and simplistic to use. It should be intelligent. So when we have data about data, we can infer certain things. We can infer schema, maybe data quality rules, ways that we want to alert and monitor, or maybe even do things like data standardization. We want to be transparent in the process and apply the right SLAs when we onboard data. And lastly is to be efficient. And I think efficiency is kind of 2 parameters into this. We want to have a high bar for data governance and data management, and a simplistic experience to introduce that. And I think there could be a thought that there's a trade-off between the 2. And the one thing I would say is we never want to compromise on the high bar that we have around data management and data governance, and that we do the hard work to bring and elevate the user experience along the way. So let's talk about the steps to onboard data. The first step is simply to register the data, the metadata about that, or the privacy and security settings. What is an actual good descriptive text that will actually tell us something about the data, so when I consume it, it can be more trustworthy and discoverable? What are the SLAs that the data producer is signing up to produce that data in? Next, for structured data, is schema design and approval. So one of the most important things, especially in a real-time environment, is when I'm producing data in real time and I'm consuming that, I can have operational impacts if some of the schema doesn't match. And this is another step that's really lends itself well to that intelligence item that we talked about earlier, where things like data standardization can be introduced intelligently in this phase. The next is the approval process, and similar to the software development lifecycle, we want to have almost the notion of like a PR approval to say, hey, this schema revision actually makes sense and can be used downstream. And then lastly is how we actually provision the data. So in our data ecosystem, we don't have just one single store that we work off of, although we do have mechanisms to drive that we'll talk about later. But there may be different consumption models. So I might produce data to the lake out of the box. I may want to add analytical capabilities. I may want to add streaming capabilities, queue-based capabilities, et cetera. But there's a cost trade-off to this too. So another step where intelligence and efficiency plays a role is to let our data producers know the cost implications of that. Next is the self-service portal in and of itself should abstract a lot of complexity from the user. And when we actually introduce a new data set into a production environment, there's actually a lot of steps under the covers that this takes. We need to provision storage and access. So that's 2 steps. But when we apply that to configuring topics in Kafka, having an analytical data that we set up, or have a queue-based consumption model, that's 3 times as many storage and access areas that we're going to have to update. We talked about approvals and version control that we'd have to set up for, and catalog updates that we may or may not have to do, business operations catalog. In some cases, this may be more than one, depending on the tools and capabilities you use in your ecosystem. So with the self-service portal, we've hydrated a control plane, which is a collection of services to configure for a data set, putting data in the right place, in the right format, at the right time. So just to call out a couple of the services in this control plane, we have our metadata and schema checks that we talked about. We configure our data quality rules, and when that data quality doesn't work, do I suppress the data? Do I quarantine it? Do I let it go through and just notify people about it? How do we transform the data? Does that happen after it lands, on the inbound? Are we executing SQL code, Python, PySpark, et cetera? That quality of service becomes really important too. So when we have a large enterprise working at trillions of event scale and petabyte scale, understanding the quality of service becomes really important, because the difference between providing P99.9 for 10 milliseconds versus 100 milliseconds is substantial. The last module I'll call out in this control plane is our observability module, where we're actually collecting metrics back from the data plane that we'll talk about later. So have our SLAs been met? Have I produced lineage? Are there alarms and monitoring that I need to put in place? So just to talk a little bit about the stack that we use here, and going back to our tech strategy that we talked about earlier, we're getting economies of scale from platforms. So when we deploy this user experience, this full stack experience to hydrate our control plane, we use other platforms to deploy our API facade and our internal web front end. Then under the covers, we use a fully serverless stack. So we're using ALB's Route 53 in an active-active configuration, which is pretty standard for what we do. And then under the covers, we're using Lambda for compute, DynamoDB for storage, and then a combination of SNS, SQS, and Lambda to communicate internally. And then one of the interesting tools I think we get a lot of good leverage out of is step functions. So as we saw a couple of slides before, there's a number of steps to actually make a data set go live. And step functions we use at scale to be able to provision, orchestrate, and synchronize those steps. But creating the control plane in a vacuum isn't enough. So as a data engineer, I could have access to the services that we lay out in our control plane, and I may integrate with each one of those services and maintain a high bar for my pipeline to generate lineage and execute data quality and do schema checks. But that's going to take time and effort to implement. And now when I have that one data engineer, and I actually have 1,000 data engineers, that point solution won't scale, and the bar that we have for data management and governance will suffer. So how do we address this? There are two approaches we use to automate our standardization and scale it. One is a central platform approach, where we simply publish data to an API, a platform enforces governance, and it puts it to one of those data stores that we described earlier, to a queue, to Kafka, to an analytical environment, to our lake, et cetera. But we found that this doesn't work effectively for all of our use cases. So we also introduced a federated model specific to our large Spark data pipelines, where instead of having a central platform to publish data through, we instrument our Spark data jobs or Spark data pipelines with a purpose-built SDK that serves the purposes of that central platform. So we're publishing data through that SDK, we're enforcing governance, but we're giving the full control of the infrastructure in Spark to those data communities that want to use that. And that's specific to our data lake pattern. And whatever the outcome of a specific organizational decision is to do central, to do federated, to do a hybrid, to do some articulation we don't have here, is that word underneath is consistency. So we've explicitly chosen to hold a high bar for governance and data management, and we've applied it consistently. All right, let's talk about our central platform to govern data at scale. Now we have our control plane that we've talked a little bit about, and we're going to introduce our data producer. So that data producer, again, could be an application developer emitting data from an API, say user logins, or a transaction, or an account update, or web logs, anything that I might want to produce in real time. Or it could be an operational data store that I want to unpack or extract. It could be a third-party file that we ingest. And there's two mechanisms to produce this data. One is to wrap one or more events into an API call. The other is to land a file for batch processing. And now we're going to introduce our data plane with API as a front end, publishing data through Kafka and Spark, and being able to get to multiple storage environments. But the data plane actually can't work in this model. We need the control plane and the data plane to be aware of each other. So those central configurations can be articulated in many ways. It can be read from the control plane. The data plane may have a hot copy. But it's important for the data plane to house those configurations and have access to those. So when a data set comes in, I can apply that set of governance. And the way that we do that, the mechanism we use is for events coming in, this front end does a lot of the legwork of the control plane articulation, right? It's doing schema checks, it's doing data quality checks, it's routing data to the appropriate place. It may do what I would call a light transform to put data into like an Avro format for Kafka, et cetera. And then for file-based submissions, we actually offload a majority of that heavy lifting to our Spark tier, which is much more suited for processing large batch data files. But as this data flows through, our data plane is also emitting data back to the control plane, that observability module that's so important. And we talked earlier about having low SLAs and real-time use cases, some that are measured in tens of milliseconds. It's important that we give that observability data back, that the data was produced in a timely manner, that the data coming in is the data going out, that lineage was produced, that data quality results are submitted. From an AWS architecture lens, we front all of this with an API layer. And again, going back to our original strategy, we try to get our economies of scale from a serverless lens, not to use Lambda, but we use ECS Fargate primarily to process this high availability, high volume API. There are a couple of components. We actually go to ECS EC2, where we really need to crank and turn the knobs for performance reasons. And then we immediately offload this data to our consumer-facing Kafka. So when we have those super low latency consumption model, we want to get that data into Kafka right away. And for all the other real-time events that we want to get into our queue-based data store or our low latency API consumption model, or to stage it into our data lake, we broadcast that through a couple layers of Kafka. And we use Kafka at significant scale. We found that to be a highly resilient, high availability, and low latency option to move data in real time at scale. Now we'll talk about our batch data pipeline, which is a pretty simple process. We're landing data in an S3 bucket. The data producer is calling an API saying, hey, this data set is ready to pick up. We process that in EMR running Spark, and again, we do all of the control plane checks and put that into our storage layer that Kajal will articulate further. One extra step that we have here is a set of Lambdas that monitor and provision EMR clusters. When we're working, again, at massive scale, where we're doing trillions of events and petabytes of data, it's really important to understand your quality of service and SLA requirements. There's a cost and performance trade-off for this. When I publish files that have low latency requirements, I want to have EMR up and running and ready to scale and to move that data quickly. But if my SLAs are 20 or 30 minutes versus 1 or 2 minutes, I may have a different treatment of that. And again, when we're working at scale, quality of service becomes very important. All right, let's talk about our federated model. So again, we have our control plane, the same control plane that we discussed earlier with our central platform solution. We're going to have our friend, the data producer. This persona may be slightly different than the one before, where they're working directly with our data lake and generating massive insight at significant scale. They're going to be have Spark expertise that understands how to use that technology and turn the knobs of the compute engine to optimize. So there's their Spark data pipeline. And you see in the pipeline, we have this SDK, okay? And that SDK is going to kind of act in that central platform capability. So it's almost an extension of the platform in a way, where it's going to gather the configurations from our control plane, metadata, data quality, transform rules, et cetera. It's going to write data to our data lake. And again, this pattern is specific to our data lake, where we put the majority of our data. And we're going to have a feedback loop to monitor the success of that data pipeline. All right, so next, we're going to have what I'll call our bad data producer. So they've not been behaving properly. They have a pipeline without the SDK, so they can't interact with our control plane. They can't write data, and they can't write back observability metrics. So the question becomes, how do we enforce this mechanism? So again, I'll go back to our original tech journey that we talked about, how we build software and how we've adopted enterprise platforms. And one of the investments we've spent a lot of time in is not just data pipelines, but our build and deployment pipelines. So we have a facade where we can build a Spark data pipeline, and we can make that whatever we want it to be. So we introduce a couple of rules that says when I deploy a Spark data pipeline, I'm going to make sure you use this special purpose-built SDK, which is, again, in a way, an extension of the platform use case that we have. And we're going to make sure that you use it in the right way. So we do some interesting code linting and whatnot to say you're using it at the right place at the right time. And again, driving consistency of that model. And then we have a special governance service under the covers that we leverage for a couple of additional steps that we have in this model to make sure that that consistent bar of data governance is met. And then lastly, we simply deploy a Spark job into EMR, Glue, Kubernetes, or some other data compute environments that we have for Spark. We write data to the lake. We send out notifications of subscriptions are applied to. We interact with our governance tier, which is one extra step. And then that whole feedback loop to our observability module and our control plane is also conducted. So the key takeaway, again, is not to be prescriptive on a central platform model or a federated model, but that word consistency. So if I decide to invest in one place, that's ideal, that's great. But I think what we've found in our data ecosystem is, maybe more than one. We don't want 10, but maybe more than one, in this case two, really is a best way to meet the use case. But that word consistency in having a standard investment that you'll do to consistently apply solid data governance and data quality and data management is the critical key here. So with that said, I'm going to turn it over to Kajal to talk about our data consumer experience.
Is that the right one?
Mm-hmm. Forward, backward.
Okay, awesome. Well, thanks, Marty. You all heard Marty talk about the data producer experience, which largely was about data registration, data publication, and data management activities. For the second part of this session, we are going to focus on the data consumer experience. And the key to making a data consumer experience simplified is to have a simplified storage strategy. So over time, our storage solution evolved through numerous acquisitions and our overall data strategy itself. As part of that, we've landed on Lake being a key strategy for enabling all sorts of shared data that is available in Capital One, in addition to a few other areas. Now, the underpinnings of this Lake strategy are three key principles. Our first principle is to ensure that we bring compute to the lake. What I mean by this is we want to reduce the storage sprawl. We want to make sure that there are as few storage solutions available as possible, because this is going to simplify our data management activities and allow us to converge on fewer storage solutions. It is also going to give our consumers the ability to point their consumption tools to S3. It will give our users the ability to point these consumption tools that are best fit for their use case, overall streamlining the experience. So that's our first key step as part of our lake strategy. One, bring compute to the lake and minimize the storage sprawl. Second part of our lake strategy, key principle, is the adoption of open table formats. So today, the data in the lake can be in structured or unstructured format. For the purposes of our conversation today, let's focus on structured format. For most part, all of our data today in the structured format is primarily used as Parquet. Now, if you think of Parquet, Parquet has several key benefits. One, it's columnar, so it allows for SQL-like access to the lake. Second, it allows you to spread your data across multiple data files. This allows for better compression ratios compared to CSV. It also allows for distributed computing because you can have multiple threads accessing this data. Lastly, it enables better data partitioning strategy. So while these are all amazing benefits of Parquet, there are some key constraints that Parquet introduces, which is Parquet only allows insert-only workloads, the vanilla Parquet. So in order to advance a lake to a strategy where it acts more like a warehouse, we need the ability to support other types of workloads, SQL workloads like deletes and updates. So hence comes the picture of open table formats. So from an open table format perspective, we have adopted Delta format as well as Iceberg. So Delta format was introduced by Databricks and made open source in 2008. Iceberg was, I believe, first brought about by Netflix and made open source about the same time in 2008. We use Delta Uniform to enable both Delta data as well as Iceberg metadata within our lake. This is, again, a key enabler for us to allow all sorts of compute to access the data in the lake, and we don't have one simple Parquet format, which, again, allows us to do various types of functions such as insert, delete, updates, because these table formats allow for maintaining transaction logs, which today is not possible in Parquet formats. Last but not least, the third key underpinning of our lake strategy is the zone strategy. So think of zone as a fit-for-purpose area to perform very specific type of operations, which allow for certain types of key access strategies, retention, and certain lifecycle policies. So a good example of this would be like a curated zone. In a curated zone, users have the ability to do schema enforcement right up front, do have the right kind of governance. Another good example of a fit-for-purpose zone would be like model build and train environment, where data scientists can load all of their data that is specific to model build and train. So a zone strategy has been key in enabling all sorts of various user-specific use cases, allowing our lake to scale. So I'll, again, kind of emphasize 3 key things as part of our lake strategy. Bring compute to the lake to allow consumption for any compute engines. Ensure open table format to make sure that we are able to do SQL-like operations in the lake. And third is introduce the zone capability for many fit-for-purpose use cases. Now, our lake platform at Capital One contains a suite of capabilities. These suite of capabilities are either invoked at design time, during data set registration, or at runtime, or during consumption. So when a user registers a data set, they also provide corresponding metadata. This metadata is registered in Capital One's metadata system. This could include something like a sensitivity indicator, the data schema, the line of business, all of these various attributes. Once the user logs this data in the metadata, a performing data steward will review this metadata and approve of the data set. Once that approval comes through, a series of provisioning activities happen. The very first provisioning activity as listed here is a service called as a provisioning service. This service has 2 key functions. The first function is for any net new data sets. It will create and identify a unique location within the lake. This unique location is based on an S3 prefix. And if you remember, I mentioned that we log a bunch of metadata when we do data set registration. So this S3 prefix, the way it's generated, is based on this unique attribute that the user provides at the time of data set registration. In addition, for any existing data sets, this provisioning service also acts as a system of record for all possible locations of this data set. So now it has performed 2 key functions. This provisioning service is nothing but a Python application that runs on Kubernetes. It uses DynamoDB as the backend data store. And then it also ultimately makes an entry in the Glue catalog for all of the partitioning information that is used at runtime. Now that once the provisioning service completes its work, the next thing is it invokes as an access management service. What does the access management service do? It allows for temporary read and write access to the data in the lake. And when I say temporary, I mean about an hour. And how do we do this? We do this by using AWS's STS token service that vends STS tokens. These tokens are only eligible for an hour. They expire after an hour. It is up to the user to renew this token. This will allow us to manage narrowly scoped data and really introduce some key data management capabilities from an access perspective. Last but not the least is our lifecycle policy. So when a data set is registered, to align with the key data management principles and to make sure that we follow our regulatory requirements, any kind of security standards, third-party contractual agreements, we need to make sure that certain lifecycle policies are defined upfront based on the type of retention requirements needed for that particular use case. At Capital One, we've also standardized the use of S3 intelligent tiering. This has allowed us to leverage all of the various intelligent tiering, like the frequently accessed, infrequently accessed, or archive instant as well. All of these three, and then we've seen massive amount of savings as a result of implementing S3 intelligent tiering. One custom solution that we have built on top of S3 intelligent tiering is also specifically for archiving entire data sets, which today is a key capability that is not available directly out of the box in AWS. This allows us to minimize the amount of fragmentation of our data set between hot and cold storage. And this is a custom solution that we've built. We do not use AWS's Glacier as part of S3 intelligent tiering. We use this custom solution and then archive it into the regular Glacier. So that's basically part of our lifecycle policy and intelligent tiering. And then lastly, we also use what is called as cross-region replication, the CRR, to replicate our data between regions. What we do, this also enables us basically to make sure our data is active, and we are able to write to both regions. We leverage replication time control, a key capability that will allow us to meet SLAs of 15 minutes or less within the lake, and this requires dedicated storage. So you kind of heard a few different suite of capabilities. I want to summarize real quick as part of our lake platform. The first is the provisioning service that allows us to identify the prefix within the S3 where the data is going to be stored. The second is a metadata service that captures all sorts of metadata that can be used at design time and runtime for schema enforcement, as well as identifying key partitions. You heard from us about the access control strategy that allows us to win STS tokens that are allowed only for a limited time, an hour, narrowly scoping the access to our data. You heard about replication and how we manage replication both for tight SLAs through replication time control, but also active writes through cross-region replication. And then we talked a little bit about lifecycle policies and how they are implemented based on specific use cases. This is our entire suite of lakes, suite of capabilities available within the lake. So now that we've talked about the lake itself and a storage solution, let's talk about our key customers. Our data scientists is one key consumer experience we'll talk about today. And then the next experience we'll talk about is our ML engineers. So as part of the model development lifecycle, it is important for the data scientists to find a place to store their model artifacts. This important storage is also necessary to allow for risk and audit processes to support the model risk governance within Capital One. So what our capability does, it allows a data scientist to use a self-service capability to provision a location for their personal space to do rapid experimentation and prototyping, as well as a collaboration space or a team space. Then an automation service runs. This automation service provides read and write access to the data. I also mentioned about lifecycle policy, that same lifecycle policy that we talked about as part of the suite of capabilities. That applies specific lifecycle policies for registered and unregistered data depending on where we are in the model lifecycle. Overall, our enterprise machine learning platform is able to now do model training, do output analysis, feature generation, all of that. And then we also apply certain scan capabilities that support a few file formats. So this is like our overall experience for our data science. As Marty said, we are heavily indexing on building self-service capabilities, allowing our consumers to be able to define their own storage solution and be able to apply all of the various lake suite of capabilities I mentioned earlier. So let's quickly look at the architecture diagram over here. There are two key things I want to point out in this diagram. One is we have, and we also talked about zones. I'm going to bring all of that together between the zones and our lake strategy. We have two key types of zones to support model, build, and train. One zone that has all of our highly sensitive data, and second zone that is our regular zone, again, both used to support our model, build, and train. We have intentionally separated this out and have dedicated AWS accounts for each of these zones. We do not allow direct interaction between our sensitive data zone and our regular dev zone. We have an intermediate zone that allows for data movement between these two zones so that our users are able to preserve the security as needed while we move the data using the data mover, which is a Lambda function. So if you think about it, we have a highly sensitive, secured environment. In this environment, we apply the same lifecycle policies, access controls that we talked about earlier. In addition to this, we also have several secure key client-side and server-side security and encryption that we enable as part of the sensitive data zone. And the second zone, again, used for model, build, and train. Similar lifecycle policies, et cetera, applied, but different type of security requirement because it doesn't have highly sensitive data. And between these two zones, we are able to talk through another zone that allows us to move the data between the two. If we scan and we find that there is some sensitive data, we do not move the data from the first zone, which has sensitive data, into the non-sensitive. So that's about the overall user experience for our model, build, and train for our data scientists. Let's talk quickly about our next consumer experience, which is a machine learning engineer. So we, again, talked about zones. We talked about rapid prototyping, experimentation, allowing our data scientists to do all of this. Now, once all of the experimentation is done, there is a need to productionalize these workloads. This is where Capital One's enterprise data platform has provisioned a low latency platform. This low latency platform allows for quick retrieval and storage of making highly available the low latent data. A user has the ability to configure this low latent data, again, through a self-service experience where they are able to create a fit-for-purpose DynamoDB. While today, we only have DynamoDB as one of the storage locations, we are looking to expand our low latency to several other types of storages as well. So now, Marty talked about the upstream data publication platform. When the data is published upstream, either through a streaming or a batch platform, this DynamoDB sync will have the ability to listen to the data that is published through Kafka, move the data into the fit-for-purpose data solution or the table that is created, and allow dynamic auto-scaling that is part of DynamoDB for our write capacity units. In terms of batch, we are able to listen to any event or notification once the data has landed in the lake. We use step functions over here to be able to pre-process the data, look at the event workload that's coming in through the batch data, identify any type of scaling that we need to do. We are not using out-of-the-box scaling functionality here because we have a lot of data that comes in through bursts, and we realized that we were spending more by just using out-of-the-box scaling. So we built our own custom solution that inspects the payload and then creates a scaling capability based on the payload. Again, we are able to do cross-region replication in the lake, so we are able to do active read and writes to both our regions. Within Dynamo, we also have a active API. It's a REST-based API that uses latency-based routing to allow us to query this data. So from an overall ML engineer perspective, we talked about few key things. We allow the ML engineer or any other user to self-service and provision a fit-for-purpose DynamoDB. We allow ingestion of data from a streaming through Kafka clusters or through batch, and we process this data both in active, and allow us to read and write data in both regions. And ultimately, we have an API that allows us to read this data based on latency-based routing. So you've heard a lot about the data producer experience from Marty, and you heard quite a bit from me on data consumer experience. So let's talk a little bit about what would be our key takeaways combining the information you heard from both of us. The first thing is streamlined experiences. In today's world, all of us obsess a lot about customer experiences. We want to bring the same obsession to our streamlined experiences to set up our data producers and our data consumers with the right data ecosystem and the tools. So hone in on those streamlined experiences. The second is mechanisms of enforcement. The key thing here is to make sure we are building for automation and we are building for scale. You heard from Marty about our ability to do central or federated data models and pipelines. You heard from me about model lifecycle policies and enabling that. These are all key examples how we are able to enforce. Next is rapid experimentation. Third key takeaway. What we mean by rapid experimentation is our ability to move quickly. We talked about a key example of data scientists having the ability to rapidly provision storage for their model build and train. And the last is unwavering trustworthiness. Our ability to make sure that our data is well governed and easy to use and easy to find and easy to consume. Thank you all for being an incredible audience. We'll take questions at the end over here.